So why are we doing this pipeline? Well, it's obviously for performance reasons. That's why people do almost everything in processors, because the faster processor generally sells more. So why are we going to pipeline? Well, if we can keep the pipeline full, we get better throughput. That is, we get more things done per unit of time. And we've seen some examples of this. So for laundry, when we're pipelined, we get one load of laundry done every hour if we keep the pipeline full. For the car, we got one car produced every hour if we kept the pipeline full. And for the MIPS processor, we can produce one instruction every cycle if we keep the pipeline full. Now we need to keep in mind that we have the same latency. So it's the same total amount of time per instruction. So for laundry, it still took us 4 hours for each load of laundry. For the car, it still took us 4 hours to produce each car, and for the MIPS processor, it still took 5 cycles for each instruction. This distinction between throughput and latency is important because in some cases you have to speed up latency, and in others it's okay to just get better throughput. So the reason this pipelining is faster is because we used all the resources at the same time. We had multiple physical resources and we used them all in parallel, and because we were using them at the same time, we ran faster. So for laundry, this was the washer, dryer, folding in the closet. For the car, it was all the parts of assembling the car. And for MIPS, we have instruction fetch, the register read, the ALU, memory, and finally writing back to the register. If we can use all of these at the same time, obviously we can do more work in a given chunk of time. So as I said before, this only works if we keep the pipeline full, and this is the hard part. We're going to see some examples in later on lectures about why this is so hard. So let's take a look at an example of pipelining performance in processors. We're going to look at a program of 3 load instructions where each one takes 800 picoseconds. So here's our program with our 3 load instructions. Now they each take 800 picoseconds, and if we run them one after each other, that's going to be 2400 picoseconds total. So if we use pipelining, we can overlap them so we use the resources in parallel, and that'll allow us to finish a lot faster. So let's take a look at that. Here are 3 instructions, and now they're pipelined in overlap so they finish a lot faster. Now there's a very important thing to notice about this figure, and that is that when I went from the single cycle implementation to the pipelined implementation, we had to make all of the stages the same length. In the single cycle implementation, the register files were much faster. They were only 100 picoseconds. But in the pipelined implementation, all pipeline stages need to be the same length, so now we need to increase them to the same 200 picoseconds as all the other parts. And what this did was it increased the length of our instructions. Our instructions now each take 1000 picoseconds instead of 800. So even though our instructions are taking longer for each one, because we pipeline them and overlap them, we're still finishing much faster. And why is that? Because we're using the resources in parallel. So if you look here we have the ALU, the register file, and instruction fetch all being used at the same time by 3 different instructions. Similarly, here we're using the register file, the memory, and the ALU at the same time by 3 different instructions. So here's a question. What is the throughput speedup due to this 5-stage pipelining? Well, it's 4 times faster. So with the pipeline, the throughput is 1 instruction every 200 picoseconds, and before it was 1 instruction every 800 picoseconds, so 4 times faster throughput. However, we increased the latency to 1000 picoseconds from 800 picoseconds, and we increased the latency because we had to balance all the pipeline stages. Also, if you look at the absolute speedup for just these 3 instructions, it's 1.7 times faster. And that's because these 3 instructions finish in about 1400 picoseconds versus 2400 picoseconds for the non-pipelined instructions. So how much faster does a pipeline go? Well, if all the stages in the pipeline are the same length, that is, it's balanced, then the time per finished unit in the pipeline is the time per finished unit in the non-pipeline version divided by the number of pipeline stages. So this is simple, and we've seen many examples of this. So the time per laundry load was 4 hours non-pipelined divided by 4 stages, which equals 1 load every 1 hour in throughput. Similarly for the car, 4 hours per car non-pipelined divided by 4 stages is 1 car every hour, so a throughput of 1 car per hour. But we didn't change the latency. So the time per laundry load is still 4 hours. Still takes 4 hours to complete each laundry load. And the time per car is still 4 hours. So pipelining has improved our throughput, but hasn't changed our latency. And indeed, if you look at the previous example, where we had to increase the processor time for each instruction, we made the latency worse due to the overheads of pipeline. And again, the pipelining only helps when the pipeline is full, not when it's filling. And we saw an example of this. So if the speed up for those 4 loads of laundry was only 2.3x, not 4x. And the reason it wasn't the full 4x is because the pipeline was not full at the beginning and end of doing the laundry. So a reasonable question here is, well, if we get an n times speed up for a pipeline with n stages, why not use a zillion stages and get a zillion times speed up? I mean, it sounds like the more stages, the better. And there are 2 main problems with this. The first thing is that most things can't be broken down into infinitely small chunks. So remember the processor we looked at before. It was pretty straightforward to divide this into 5 pieces. It would be really hard to divide this into 100 pieces. So, what about the ALU or the register file? Can we chop those up into smaller pieces? So that there's a practical limit to the logic design in terms of how much we can cut things up. There's also an overhead for every stage. So we need to store the state for each stage. That is, we need to keep track of which instruction we're processing in each stage. And this means we need a register, and each register takes some time. And what we'll see in later lectures is that the longer the pipeline is, the harder it is to keep fill. So then you'll get less performance as well. So now we're going to talk about pipeline registers and overhead. So before we get to there, let's talk about what's in the pipeline. So each pipeline stage is combinational logic. So think about what it's doing. It's an ALU that's doing an addition, or it's a sign extension unit. These are combinational logic. What we need to do is we need to store the state for each stage. So each stage needs to know which instruction it's working on, and this needs to be stored. So we're going to have combinational logic in the state, and we're going to have state for storing for each stage. So how do we do this? Well, we put pipeline registers between each stage, and they store the instructions. So let's take a look at some examples. So if we have a non-pipeline processor, we put in an instruction, 100 nanoseconds later we get out the result. So we get 1 every 100 nanoseconds. If we have a pipeline processor where we ignore the overhead of the pipeline registers, well, we put in an instruction, we've pipelined 5 times, so each pipeline stage takes 20 nanoseconds, and when we're done, we get an output 1 every 20 nanoseconds, so 5 times faster. If we look at what happens when we have a real pipeline with registers, first we put in our instruction, we go through our combinational logic of our pipeline stage, then we need to store it into a register. Storing it into the register takes some time. And then the rest of the stages are also going to need to store into a register. And so what we see if we look at the cost of the pipeline registers is here we're getting 1 output every 22 nanoseconds. So this is only 4.5 times faster. That is, we spent 10% of our time in the overhead from the pipeline registers. So from this example, you can see that if I had 1 million pipeline registers, I'd spend almost all of my time in pipeline registers and very little time actually doing work. So it would be very inefficient if I have too many pipeline registers. Now let's talk a little bit about clocking so you can see how these registers work. So the clock speed is determined by our critical path, and the critical path is going from one register through the combinational logic in the pipeline stage to the next register. Let's take a look at this stage in particular. So the first thing that happens is the clock comes by. And when the clocks come by, the first pipeline register is going to take its inputs and move it to its outputs. Now at this point we're ready to process. Now the data can go through the pipeline stage, this is the combinational logic, and process the results. This is the part that takes 20 nanoseconds from our stage. Now we've got our result, and our result is waiting to go on to the next pipeline stage. And it needs to be here before the clock, because at the next clock, that data is going to go through the pipeline register onto the next stage, and then from there it can go on to compute the next stage. So this clock needs to be slow enough so that you can both take the time between the stage, that is the combinational logic of the pipeline stage, 20 nanoseconds here, and the time of the pipeline register, this 2 nanoseconds. And that means that if our pipeline registers take 2 nanoseconds and each stage takes 20 nanoseconds, our clock can't run any faster than 22 nanoseconds. So that's how the delay of the pipeline registers gets in here. So let's talk a little about ideal pipelines in reality. So in reality, not all stages are the same length. And what this does, it forces the clock to be as slow as the slowest stage. And we saw an example of this when we looked at the processor. There are overheads for long pipelines. It's hard to chop up the work, and the pipeline registers take some time. And it's also hard to keep the pipeline full, and it's very hard to keep the pipeline full if it's a long pipeline. We'll see more about this in the later lectures. So a question, what is the speed up for 10 pipeline stages? Well, this is straightforward. It's 10 times faster. So instead of producing a car every 4 hours, we'll produce a car every 4/10 of an hour, which is 10 times faster. But it's still going to take 4 hours per car. We've now got 10 stages that each take 4/10 of an hour. Another question, what if you have a non-pipeline instruction that takes 120 nanoseconds, and the instruction is pipelined with 10 stages, but each pipeline register takes 6 nanoseconds, what is the overhead of the pipeline registers? Well, it's going to be 33%, and we can see this from a picture. So here's the non-pipeline version, and here's the pipeline version. So in the pipeline version, we have 10 stages, and in each stage we spend 12 nanoseconds on the logic and 6 nanoseconds on the register. So now we're getting one output every 18 nanoseconds, which is 6.7 times faster. It's not the 10 times faster that we'd expect, so this is a 33% overhead from the pipeline registers.